This is Exploring Point Groups Part 2 of Symmetries, Solids, and Coordinates. This is Math 4250 at the University of Georgia, and I'm Dr. Jason Canarella. A regular solid is a convex polyhedron where, number 1, all faces are identical, regular polygons, and 2, the same number of faces meet at every vertex. So here they are. There are only 5 regular solids in three-dimensional space. They are the tetrahedron, triangles meeting in threes, the cube, squares meeting in threes, the octahedron, triangles meeting in fours, the dodecahedron, pentagons meeting in threes, and the icosahedron, triangles meeting in fives. The stick is not a regular solid. The regular solids are beautiful shapes, and we can see by looking at them that they have lots of interesting symmetry. In this orientation, we see that they have rotational symmetries around the z-axis, though they have symmetries around other axes as well. But what if you actually wanted to build these shapes as coordinates? The only regular solid whose coordinates are really obvious is the cube. If we look at this picture, we can see that each coordinate is plus or minus a half, and that the 8 vertices of the cube represent all possible assignments of pluses and minuses to the 3 different coordinates. 2 signs for the x-coordinate times 2 signs for the y-coordinate times 2 signs for the z-coordinate is 8 vertices, 2 to the third, altogether. The coordinates for the tetrahedron and the octahedron, and especially the icosahedron, are simply a giant mess. Looking at this, we can see no obvious pattern. Recall from last time, we had 2 matrices, A and B. We'll write out the entries of the matrices A and B. There's B. And here's A, but that's not the best way to think about them. A is a rotation by 120 degrees around the 1, 1, 1 axis, and B is a rotation by 180 degrees around the 0, 0, 1 axis. All products of A and B form a set of 12 orthogonal matrices. This set is a point group, or symmetry group. Now, each matrix in the group is a transformation of space, so it moves a point to somewhere else. Now we introduce a really beautiful definition. The orbit of a point X under the action of a group G is the set of points Gx for all elements little g in the group G. As an example, we're now going to look at the orbit of the point 111. First under B, then following B by A, and then following that by another A. The 4 points we get form the vertices of a tetrahedron, and we can label them P, Q, R, and S. These coordinates make much more sense than the standard coordinates for the vertices of the tetrahedron. This still leaves us with a mystery. Why are there 4 points and not 12? We now look at applying all 12 of our matrices to this tetrahedron. We'll see that some of our transformations fix one of the points. The presence of these fixed points mean that the orbit has fewer than 12 points in it. In fact, exactly 4. Next, we'll look at the orbit of a generic point in the form 1x, 0. We can bring some order to this cloud of points by observing that they fall on the vertices of 3 rectangles. Notice that while the entire configuration of 3 rectangles is preserved by each of our 12 transformations, no individual point is fixed by any of them. That is why the orbit of this point contains 12 points, whereas the orbit of the special point 111 only contained 4. We'll next see the orbit of an entire line segment, the line joining 1x0 to 01x. Notice that since our transformations are orthogonal matrices and hence isometries, the length of this segment is preserved. This means that the 12 images of the line segment will form the sides of 4 equilateral triangles. The triangles will have the same symmetries as the entire configuration. 12 different rotations around the same collection of axes. The orbit of the line joining 1x0 to 01 minus x has the same property. it creates a configuration of 12 equal line segments forming the sides of 4 equilateral triangles. The 4 equilateral triangles also have the full collection of symmetries. The configuration of red and blue triangles forms a shape whose beautiful symmetries allow it to be used in the construction of this symmetric tensegrity. We can see in the tensegrity that the dowels are connected by pieces of elastic cord, and the symmetry holds the dowels firmly in place despite the fact that they don't touch each other. While the symmetry of this real tensegrity isn't perfect, we can still highlight the triangles on the shape, which would correspond to the blue triangles in our ideal orbit. Filling in the remaining triangles with green, we see that the full configuration consists of a mix of equilateral and isosceles triangles. As we vary the value of x, we get a family of shapes. Their vertices are all orbits of 1x0, giving them a beautifully structured form. And each of these shapes shares the full 12-element symmetry group. When x is 0, we recover one of the regular solids, the octahedron. Here its coordinates are much more understandable than in the usual form. Again, since the octahedron is part of our family, it shares the full 12-element symmetry group. At the end is called the cuboctahedron. The cuboctahedron is constructed by taking a cube and measuring to the midpoint of each edge. We then cut the corners off by planes passing through those midpoints and delete all the corners in turn. This leaves us with a new shape. Again, the coordinates of our solid obey a beautifully structured pattern, and the solid shares our full 12-element symmetry group. If we choose just the right value of x, we can stop the evolution when the green triangles are also equilateral. At this point, the green, blue, and red triangles are all identical. But this shape is the icosahedron. Because we've built it this way, we see its coordinates in a simple form, which makes much more sense than the standard presentation of the coordinates of the icosahedron. As before, the icosahedron shares our 12 symmetries. But these are not all the symmetries of the icosahedron, because these symmetries preserve the red, green, and blue triangle partition. The new symmetry, a rotation around a different axis, exchanges red, green, and blue triangles. Adding this rotation to A and B, we can generate a group of 60 rotations, often called the icosahedral group. Well, the oriented icosahedral group. But that's a subject for a more advanced class. Or is it? Thank you for watching. Now do your homework.